Something extraordinary is happening in China that will forever change how we move around the planet. Can you imagine traveling faster than a commercial airplane but on land? China has just achieved it. Chinese T-Flight Maglev, the 1,000 kilometers per hour monster. We start with something that has just completely changed the rules of ground transportation. The Chinese T-Flight Maglev reaches 1,000 kilometers per hour, a speed that makes a Boeing 737 during takeoff seem slow. To give you an idea, a commercial airplane flies at about 885 kilometers per hour. This train surpasses that on land. How is such speed possible? The key is that this train never touches the tracks. It floats completely in the air using powerful magnets that lift it above the track. By not touching anything, there's no friction to slow it down, allowing speeds impossible for traditional trains. It's like a bullet fired through a magnetic cannon, except the bullet is a train full of passengers. CR-450, the Aerodynamic Sword. Trains have evolved significantly since their early days when steam engines first appeared. Reaching 48 kilometers or 30 miles per hour was considered fast. This was a big improvement over horse-drawn carriages. In 1964, Japan introduced its first bullet train, the Shinkansen, which could travel at about 210 kilometers or 130 miles per hour. This was a game changer, allowing people to cover long distances in much less time. More recently, in 2004, China unveiled its first commercial maglev train in Shanghai, hitting speeds of 460 kilometers per hour. At the time, this was revolutionary. The train connected Pudong International Airport to the city center in just 8 minutes, covering 30.5 kilometers of track. But for China, this was just the beginning. CR-380D, the Silent Dragon. Magnetic levitation, or maglev, begins with a simple but radical idea: eliminate contact with the track. In China's new generation of high-speed trains, this is achieved through electromagnetic suspension, known as EMS. Here, the train floats just a few millimeters above a specially engineered rail, held up by powerful magnets and controlled in real time by advanced electronics. The absence of wheels means there's no rolling friction. Only the resistance of air remains. This tiny gap, often less than 10 millimeters, is maintained by a constant dance of magnetic forces, responding to thousands of adjustments every second. The 650 kilometers per hour breakthrough. But the real secret to achieving these extreme speeds lies in the vacuum tubes. Imagine this. While other trains constantly fight against the wind, the T-Flight travels inside tubes where there's almost no air. It's the same principle that allows spaceships to travel so fast. Without air to slow you down, you can reach incredible speeds. The result is striking. This train is capable of covering the distance between Beijing and Shanghai in less than 2 hours, a journey that normally takes 4.5 hours on the world's fastest trains. Without doubt, this speed is completely redefining what it means to travel on land. Maglev technology explained. So what exactly is maglev technology? Well, maglev stands for magnetic levitation. It's a method of transportation that uses powerful magnets to lift and propel trains. Instead of using wheels on a track, these trains float on a magnetic field. The concept of magnetic levitation isn't exactly new. It's been around since the early 20th century when Robert Goddard and Émile Bachelet first proposed using magnetic fields for transportation. Now let's break it down. How this system actually works. Traditional maglev trains float about 10 millimeters above the track. However, this new system levitates 100 millimeters. That's 10 times higher. This increased height reduces interference and allows for more stable operation at ultra-high speeds. The test track. Breakthrough. On a humid morning at the Qingdao test site, a team of engineers gathered in the control room, eyes fixed on a wall of monitors. The prototype Maglev, built with a carbon fiber shell and loaded with sensors, waited at the far end of the track. Lead engineer Dr. Liu from Southwest Jiaotong University recalls the tension before the run. The previous month, a resonance issue had forced an emergency shutdown at 590 kilometers per hour. Now, after weeks of recalibrating coil arrays and refining the active damping system, the team was ready to push beyond 600. The train accelerated with a low, steady hum, gliding above the guideway on a cushion of magnetic force. Within seconds, the digital speed readout climbed past 600 kilometers per hour. Data streams showed vibration levels holding steady, the carbon fiber body flexing within safe limits. The record-breaking run. In sixth place, we have something that marked a before and after in Chinese railway history. The CR380D was the first train built completely with innovative Chinese technology. While previous models used German and Japanese technologies as a base, this monster is 100% Chinese design and engineering from scratch. Its most striking feature is something you'd never expect in a high-speed train. It's practically silent. While other trains sound like fighter jets, the CR380D passes like a ghost. You can stand next to the tracks and barely hear a whisper when it passes at over 350 kilometers per hour. The Donghu Laboratory success. During the test, they focused on several key aspects. First, controlled navigation at such high speeds. Even the slightest deviation could be catastrophic. The system needs to be able to keep the train on its exact intended path with incredible precision. Second, stable suspension. The train needs to maintain a consistent height above the track without any wobbling or fluctuations. This is crucial for passenger comfort and safety. Finally, safe stopping. Being able to go fast is one thing, but being able to stop safely is just as important. The test demonstrated that the system could bring the train to a controlled stop from high speeds. These tests have proven that the basic concept works. The next step is scaling it up to longer distances. Environmental impact. Measured by carbon output, the difference between maglev and air travel is striking. On current test runs, China's maglev trains generate an estimated 10 to 25 grams of CO2 per passenger kilometer, a figure that reflects both the efficiency of electric propulsion and the country's evolving energy grid. In contrast, short-haul jets on routes like Beijing to Shanghai typically emit between 90 and 130 grams per passenger kilometer. These numbers depend on factors like train occupancy and the mix of renewables and fossil fuels in the grid. But even under conservative assumptions, maglev's footprint is a fraction of aviation's. An environmental analyst from the International Energy Agency points out that as China's grid shifts toward more renewables, the emissions gap will only widen. The passenger experience. The Shinkansen E5 isn't just a train. It's a lesson in perfection applied to mass transportation that has left the entire world speechless. This legendary bullet train is Japan's fastest commercial train, reaching 320 kilometers per hour. But its true power isn't just in speed, but in something no other railway system has managed to equal. Its punctuality is absolutely precise. The average delay is only 18 seconds per year. It's perfectly designed to maintain exact schedules with each component calculated to function like a Swiss watch on rails. The Japanese have achieved something that seemed impossible: 60 years of operation without a single fatal accident. Practical applications. Let's talk about what this means in practical terms. This kind of speed could create what economists call one-hour economic circles, massive urban clusters where any 2 points are no more than an hour apart. This could completely change how people live and work. Imagine being able to live in one city and commute to work in another city hundreds of kilometers away. It could make long-distance relationships a whole lot easier too. Cities that are currently hours apart could become as connected as different neighborhoods in the same city. There are also some significant environmental benefits to consider. If these trains can replace short-haul flights, we could see a substantial reduction in carbon emissions. The financial commitment. China's commitment to maglev technology is measured in billions of dollars. The national goal is clear. By 2035, a high-speed network will connect major city clusters, linking maglev lines seamlessly with existing bullet trains. Funding for these projects comes not only from state budgets, but also from public-private partnerships, with estimates ranging from $11 to $18 billion invested by 2025. This financial firepower is matched by a global rivalry. In Japan, the SC Maglev project holds the crude speed record at 603 kilometers per hour. While Germany's Transrapid technology once set the commercial benchmark, China's CRRC aims to surpass both, not just in speed, but in market reach. The challenges ahead. Japan has completely revolutionized the concept of rail transportation with its innovative L0 series maglev, capable of reaching an impressive 603 kilometers per hour and defying all laws of conventional ground transportation. Although it's not yet commercially operational, it's expected to enter service in 2027 and promises to change everything we know about traveling on land. This revolutionary train uses a superconducting magnetic levitation system that keeps it floating 10 centimeters above the tracks without touching absolutely anything. Its suspension technology is so sophisticated that it can maintain perfect stability even at speeds exceeding 600 kilometers per hour. Infrastructure complexity. But let's pump the brakes for a second. As cool as all this sounds, there are some significant challenges to overcome. For one, the infrastructure costs are enormous. Building low vacuum tubes over long distances isn't cheap, and integrating this system with existing rail networks is a complex task. To give you an idea, the cost of building conventional high-speed rail lines can range from $17 million to $170 million per kilometer, depending on the terrain and other factors. A maglev system in a vacuum tube would likely be even more expensive. We're talking potentially hundreds of billions of dollars for a single long-distance line. Safety considerations. Building and maintaining near-vacuum tunnels hundreds of kilometers long demands unprecedented precision. Each segment, often 6 meters in diameter, must align within millimeters to prevent leaks that could compromise the entire system. The energy required to sustain low-pressure environments and keep superconducting magnets cold adds another layer of cost and complexity. Land acquisition along busy corridors like Shanghai to Beijing has sparked disputes with local governments and property owners, raising questions about social and financial feasibility. Safety certification for passenger travel at 1,000 kilometers per hour remains undefined, with no published protocols for emergencies or rapid decompression inside sealed tubes. Global competition. We reach third place with the German ICE-3, Europe's fastest train that maintains the reputation of the nation that invented magnetic levitation. This beast reaches 368 kilometers per hour in tests, though it operates commercially at 300 kilometers per hour for safety reasons. Its real secret isn't in pure speed, but in something revolutionary. It's practically impossible for it to derail. The ICE-3 uses distributed traction technology that allows it to accelerate and brake more efficiently than any worldwide competitor. Its active tilting system allows it to take curves at speeds that would instantly derail other trains, but it maintains perfect stability thanks to sensors that constantly monitor track conditions. The Hyperloop comparison. In the United States, several companies are working on Hyperloop technology, which shares some similarities with the Chinese Maglev system. While progress has been slower, there have been successful tests, and several states are considering Hyperloop projects. The main difference between Musk's Hyperloop and China's T-Flight lies in their design and goals. Both are high-speed transportation concepts, but they take different approaches. The Hyperloop aims for speeds of 1,200 kilometers or 760 miles per hour using pods in a low-pressure tube, while the T-Flight targets 1,000 kilometers or 621 miles per hour using maglev technology in a tube that doesn't need to be near vacuum. China's new trains aren't just faster than planes, they represent a fundamental transformation in ground transportation technology. From the 1,000 km/h T-Flight to the silent CR380D to the perfectly punctual Shinkansen E5, these machines prove that the future of travel isn't in the sky, but on magnetically levitated rails. As vacuum tube technology matures and infrastructure expands, the era of supersonic ground transportation is arriving faster than anyone expected. The trains of tomorrow are already here, and they're faster than you ever imagined possible.